Welcome back, Geos 406 students. For this week's module, we're going to be working with volcano hazards and risk, and we're going to formulate some simple probabilistic forecasting and estimation of hazards and risk for a volcano in the Philippines, Mount Mayon. So we'll talk about what hazard means versus what risk means. We'll talk about some types of hazards, primary hazards, lava flows, ashfall and tephra, and pyroclastic flows in particular. You'll work a little bit with hazard maps and with estimating probabilities of future hazards for an eruption from a given volcano at a location around that volcano. Using Mayon, it's sort of a hypothetical situation of Mayon volcano in the Philippines as an example. So on this slide, I have a cartoon from the Auckland Civil Defense, which shows a cinder cone eruption happening in a suburban neighborhood in Auckland. And before you think, wow, that's really far-fetched, it's actually not that far-fetched. Auckland is a city that's built around a cinder cone field, and it's not inconceivable that in the future you might have an eruption from a new vent pop up somewhere within that city. So in this slide, you can see this ash cloud and Hawaiian lava fountaining happening, Strombolian explosions right here. This is the hazard. So what's coming out of the volcano, the hot avalanche of bombs, lava flows, ash, those pose a hazard. The risk is what happens to the people surrounding that hazard. So this area you can see around here is at very high risk for negative impacts from this eruption. Whereas if you look way, way, way across the bay, way over here somewhere, those houses are at low risk. So a hazard is a natural or human-caused process that has the potential to cause destruction, whether humans are threatened or not. The hazard's always there. Risk, however, describes the effect that those hazards may pose for people. So that means that if you're way far away from an erupting volcano, you're at very low risk. If you're right next to the erupting volcano, like in this neighborhood in Auckland, then you're at very high risk for some destructive impacts from that eruption. So hazard maps are based upon the extent and type of hazardous deposits that occurred from past eruptions. And on this slide, I show an example from Mount Rainier. This is a hazard map that's produced for the public by the USGS for Mount Rainier. You can see the mountain here. The gray areas around the mountain immediately adjacent to the vent of the volcano are areas most likely to be affected by lava flows and pyroclastic flows from a future eruption of Mount Rainier. However, the main hazard to people around Mount Rainier, apart from ash fallout, is lahars. Mount Rainier is very good at producing lahars. You don't even have to have an eruption for Mount Rainier to produce voluminous debris flows and lahars. Some of those lahars can travel all the way through towns and cities out to Puget Sound, through some highly populated areas downstream of the volcano. So this map shows intervals of lahar reoccurrence. The orange are small lahars, so they happen pretty frequently, definitely less than 100-year recurrence interval. So that's shown in these darker orange areas, pretty close to the volcano. The medium to light colored orange are moderate lahars, so these happen every 100 to 500 years, and you can see they go pretty far. They travel through towns in all directions away from the volcano, including downstream, through Orting and through Tacoma to Puget Sound. And then yellow lahars, those are the truly catastrophic large lahars. They happen every 500 to 1,000 years, and they cover a very wide range downriver of the volcano. So these maps give the best estimates of a forecasted extent of future hazards from a volcano. They can be fieldwork-based or model-based or both. Usually you need the fieldwork to verify the model anyway, so fieldwork is a very important component of mapping hazards around a volcano. Maps are usually made to convey the most possible information in a very simple, easy-to-read format, and they must be widely understandable to the public. Because if you live in Orting, you're going to want to know what the deal is with the lahars from Mount Rainier, how you're going to be warned, where you're going to need to evacuate, how often you can expect these things to occur, how big they are. So let's talk about different volcano hazards. The first come from lava domes and lava flows. And you know already what lava domes and lava flows are, but you know that they carry hot molten rock far away from the vent. In the case of low viscosity basalt lavas, they can move very fast, as in the case of Goma. Lava domes form when lava piles up over the vent, and they can collapse and cause deadly pyroclastic flows. Tephra, or ash fallout, can be carried aloft and blown downwind. They land out downwind of the volcano, as you know. They can travel hundreds of thousands of miles. They impact people's health. They can collapse building roofs. They are very, very damaging to aircraft. Pyroclastic flows, these are high-speed avalanches of hot rock, gas, and ash. They can form by collapse of lava domes or eruption columns. They're very hot, they're very fast moving. They travel down river and stream valleys, but they can burn things outside of those confines for a wide swath. They're very destructive. Debris avalanches and lahars, as you know, are landslides of rock, soil, water, vegetation. They move pretty quickly. They can bury and carry away or destroy things in their path. They can travel very far away from the volcano, and they can be very deadly. So basalt lava flow hazards, typically what happens is like what you see in this picture here from Hawaii. You have lava flows that have covered a road, basically cutting off and isolating the neighborhood that was served by this road. Usually in Hawaii, the lava flows just destroy things. They move slowly enough so that people can get out of the way. Most often, but you can't move a road, you can't move your house. So lava flows can be very destructive. I have some LinkedIn videos in the Blackboard course materials area that you can watch to see destruction caused by lava flows. We know most recently that in Hawaii in 2008, the eruption of the East Rift Zone from Kilauea caused a massive amount of destruction to people living near the fissures that were opening up, that were allowing basalt lava to erupt and flow away from the East Rift Zone. So lava flows can burn houses, they can bury houses, they can destroy forests, etc. You get the picture. If you have basaltic lava that otherwise would have erupted quiescently, but it erupts underneath a glacier, you can melt the glacier with the lava, creating energetic phreatomagmatic or hydrovolcanic explosions. Iceland is a great example of this. You can see from this photo, you have a gaping hole in the middle of your ice field where you have an eruption occurring, spreading ash around that vent. You can get Yokalop's big catastrophic glacier-fed floods from that. So I talked about this during the lava flow lecture, just to remind you that sometimes lava flows can actually be deadly. And Nyiragongo erupted in January 2002, produced destructive, fast-moving lavas. You can see this lava piled up here where the boy's walking. This is along the airport at the runway. You can see lava filling one of the streets of town, flowing through the gates of this residence. You can see another view of that lava flow flowing through the streets of town. Here. If you look at a map, here is Goma is down here. The airport is right here. You can see it on this other image where it's not annotated with where the lava flows went in red. Here's the airport. You can see that the Nyiragongo crater is up here in the upper part of that image. You have these yellow outlined fissures coming away from the volcano. Those fissures were feeding the lava flows. And one of them opened up really close to town. So it was right here. It was just not that far away from the airport, maybe just 1 to 2 kilometers away from the airport. That lava was very fast moving, and this fissure opened up so close to town, the lava flowed through the town before anybody had any warning. So this is a very interesting situation. It presents a really interesting hazard situation because it's not very easy for scientists to enter areas in the Democratic Republic of Congo because of civil unrest and political unrest. But you can map a lot of these things using satellites, which is pretty great. So this probability map here was made based on satellite imagery mapping these flows and from prior flows, and it shows probabilities of where lava flows will go from Nyiragongo through the populated areas around Goma. So here's the Nyiragongo crater. You can see it's a sort of a series of 3 craters. Fissures extend away from that crater down towards Goma. and the different zones are mapped out in different colors. So probability of lava flow invasion in the blue areas is really low based on history. There aren't a lot of lava flows that went around the light blue areas. The green areas are a little bit higher. We know there are lava flows around there, but they might be old and they don't reoccur very often. The yellow areas have an intermediate probability. Orange areas are a slightly higher probability. And when you get up to red and blue, we're at really high probability. So red is a 3 to 8% chance of lava flow inundation in the future. And blue is 8 to 20%. So you can see the highest hazard areas from Nyiragongo for lava flow invasion they go right through town. So in this one-day-long eruption in 2002, fast-moving lava flows destroyed about 15% of the Goma city. Rifting propagated new fissures into town from which the lava erupted. And there was very short notice. There was really no monitoring in the area. And some people actually lost their lives, which is very unusual for basalt lava flows. Usually you have some warning. The very high probability hazard zone still exists running through the main part of Goma, so next to and over the airport and other major city facilities. So here are some pictures. The lower one is actually a clip from Google Earth. The upper one is from a prior publication. The lava flow ran across part of the main runway at the airport, and you can see that right here. The fissure opened up right outside the airport, and lava poured out of that fissure and ran right over the end of the runway, which is right here, and then it kept flowing right through town. You can see the path of the lava flow in this picture here. From this oblique aerial photograph, it flows right through town, and you can see this dusty brown surrounding these houses is where the lava flow basically flowed right through the city. So in Google Earth, this is September 2010 image, less than 10 years post-eruption. I clipped this out of Google Earth and I made a trace here showing where the lava flows went downstream of the fissure. And you can see that the city's largely rebuilt right over that lava flow pathway. But if you remember, the probability estimate is 3 to 8% that you're going to have a future lava flow inundation event in this area. That's actually really high. So it's very likely this is going to happen again. If we zoom in, you can still see some remnants of that recent lava from 2002. But you can see that the houses are largely rebuilt in this area, or they're largely being rebuilt. All right, so ash fallout from ISOPAC maps. The ISOPAC maps that you worked on for your Module 5 actually are useful as a hazard forecasting tool and a hazard map tool. So ashfall impacts people downwind. If the wind speed is sufficient, you can be upwind, right, and have no ashfall or very little, but you could be downwind and receive great amounts of ashfall. So these ISOPAC maps can be used to construct hazard maps for ash fallout. And when you're in areas where the prevailing winds don't change all that much in direction from season to season or year to year, past ISOPAC maps can be very useful for hazard forecasting information. All right, so here's Vesuvius again. I showed you these ISOPAC maps and this lithograph in prior lectures. So here's Mount Vesuvius, and from 79 AD eruption ISOPACs outlined in white and gray in this ISOPAC map. You can see 100 centimeter accumulations pretty far downwind, 10 centimeters and 10 centimeters out this far. So basically this whole area that is now populated by the modern day, it's really kind of an extension of Naples. It's a lot of little towns connected together, but it's kind of one big city. They're at risk for great amounts of ashfall in the future. Upwind, very little ashfall is expected. Downwind, accumulations can be really heavy. In Alaska, this is a map by the USGS, you can see that our prevailing winds make it so that ash fallout on the Kenai Peninsula and Anchorage area is really common. So winds in Alaska travel from west to the east or from the southwest towards the northeast. Our active volcanoes in Cook Inlet, Spur, Redoubt, and Augustine erupt pretty frequently. And you can see where Anchorage is, you can see where Kenai Peninsula is, where the majority of the population of Alaska lives. More than half of the population of the state lives in this general Anchorage-Kenai Valley area. And you can see the isopachs from Mount Spur travel to the east, Mount Redoubt travel to the northeast, Augustine towards the east-southeast. And you can see that fallout from these eruptions will, impact these towns downwind of the volcano repeatedly. So this is what we can expect will happen in the future as well. Nova Repta here is a very specific case. That was the 1912 eruption that was a VEI 6. It was a very huge catastrophic eruption. It deposited ash over this very broad area. Dawson received ash, Juneau, Ketchikan, Vancouver, Canada, and even Seattle, Washington had recorded measurable ash from that eruption. So ash is really heavy. It's pulverized rock, and I'm going to show you this graph here after the USGS website publication shown down here to give you an idea of how much ash loads roofs. So 10 centimeters of snow and 10 centimeters of volcanic ash, you can compare those directly. If you're in Alaska, you know what snow load looks like. So new snow has a density of 50 to 70 kilograms per meter cubed. The load is about 0.05 to 0.07 kilopascals. So that's the amount of load on your roof. So if you get 10 centimeters of snow, your roof is going to get this much load on it. Damp new snow, so wet snow, is going to be more dense. It's going to have about 2 times the load. Settled compacted snow is going to be even more dense, and it's going to have, yet again, another 2 times that load. Dry uncompacted ash is pulverized rock. It's not water. It's much more dense, 500 to 1,300 kilograms per meter cubed. That means the load on your roof is going to be 0.5 to 1.3 kilopascals, much greater than the same thickness of snow. Wet compacted ash is very dense, it's very heavy, it's very wet, and the load will go up again by 2 times. You can calculate load on your building given this equation. So if you're curious about doing some more calculations to see what the loads are like for different ash densities, feel free to play around with that. So this graph illustrates some of the differences. Dry uncompacted ash is shown here by these diamonds. Ash thickness in millimeters is on the y-axis, and the load in kilopascals is on the x-axis. You can see that for dry uncompacted ash, you need pretty good amounts of thickness to reach loads of 2 kilopascals, right? So that's 400 meters or 400 millimeters of ash is needed for a 2 kilopascal load. If you have dry compacted ash, you don't need nearly as much. 2 kilopascals a load, you need half the thickness or 200 millimeters of the dry uncompacted ash comparison. Wet ash, 2 kilopascals, you can get that with even just a little more than 100 millimeters. So that's 10 centimeters right there. It's about 6 inches of wet compacted ash will create a huge load on your roof. Roof collapse happens right around the 1.5 to 2 kilopascal load threshold. All right, so here is a table that shows from Rabal 1994 ash thickness in millimeters versus estimated load versus observed damage to the roofs. So at the lowest amount of load, less than 100 millimeters of ash, most everything was intact. When you get up to 300 millimeters of ash, your load is huge. So more than 50% of roofs survived, but a little bit more, and you got more than 50% of the roofs actually collapsed. So this actually just gives you some idea of how much ash it takes to actually create damage to buildings. So these pictures from Clark Air Force Base show some examples of this. So in June 15, 1991, Pinatubo erupted 5 to 10 centimeters of wet ash at former U.S. Clark Air Force Base, which was 20 kilometers northeast of the volcano. The densities of ash in this case range from 1,200 to 1,600 kilograms per meter cubed dry, or 1,500 to 2,000 kilograms per meter cubed wet. So in this case, 16% of short span roofs, so that would be like a house shown here, There's short spans between the supporting members supporting the roof. So 16% of those roofs suffered major damage, but 43% had actually no significant damage. But long span roofs, so that would be like an airplane hangar, like shown down here, a gymnasium building. So that's a roof with a big open empty cavern inside that has few supporting members of the roof in between. 75% of those long span roofs were severely damaged.